to start on time. So it's a great pleasure to welcome back Andrea Cavalleri. So Andrea is the founding director of the Max Planck Institute for the Structure and Dynamics of Matter, and also professor at Oxford. And he had a distinguished career in starting with a PhD in Essen, then a postdoc in San Diego, and then stay in Lawrenceburg, the lab. So, you know, like in for entrepreneurs, they're very proud of their motto. How do they say? To do things fast and break things. So Andrea is kind of the opposite. He does things fast and he makes things. You know, so he has really excited many of us by sort of starting by doing ultra-fast probes and observing new phenomena. So just to mention a few, he was one of the first to generate femtosecond X-rays and to observe real-time atomic structural dynamics, to have photo-induced phase transitions, and most recently by, again, applying radiation, which naively should, you know, just hit the samples and destroy any kind of interesting type of order. He demonstrated that he can induce ordered state at temperatures which are 5 times higher than ordered states. So he is recipient of many prizes. I'm not sure I will go through all of them. Isaacson Prize, Max Born Medal and Prize, Daniel Kahneman Prize. So, okay, probably should just shut down and let Andrea say. So it's a great pleasure. So it's always stimulating to have him, and I'm looking forward to the new subject which he will tell us about.
Many thanks. Very good. Thank you very much, Eugene, for this introduction. Thank you for having me here and coming to the talk. So I've been here at least twice in the past few years, and I seem to always be talking about the same thing, which are experiments in which we've been studying the light-induced generation of superconducting fluctuations above the thermodynamic transition temperature. So I thought today maybe I'll talk about something slightly different. And this is a topic that I talk about rarely, but I really do find very interesting. And it's about the use of terahertz light to study the interlayer tunneling between layers of superconducting cuprates, and to look at the nonlinear response. This is something that, as I said, is a topic that I seem to be the only person interested in it, but I really find it quite nice. And so let's see. I'm not sure whether this is the best way to start a talk about this, but I am just going to say. But you know, we are interested in the nonlinear response at long wavelengths of quantum materials, and we're just going to give my own operational definition of a quantum material as a material in which has a macroscopic behavior which cannot be understood without quantum mechanics. Obviously, you know, if you think about a metal or an insulator, you can't get things right quantitatively without thinking about quantum mechanics. But you can kind of believe that, you know, even non-quantum mechanical electrons could be localized or not localized for various reasons. And in some limits, you could get something that makes some sense. But obviously, things like a superconductor, I think, are states in which even qualitatively you're not able to explain basic phenomena. Even qualitatively without quantum mechanics. So the idea is of these experiments are about to, you know, these materials are studied routinely in using a number of probes, typically close to linear response. We study optical spectra, Raman spectra. We look at the way neutrons or X-rays scatter from them, and we try to interrogate the response of these quantum materials. But there's clearly a lot of science to be done if you're careful, where you try to look at the nonlinear response of these elementary excitations and collective cooperative quantum phenomena. So one goal, which I won't talk about too much today, will be to reveal and create functionalities that are not present at equilibrium but that are hidden, but also a subset of things that I will tell you about today is how I will be able to sometimes reveal some aspects, some things that are there but cannot be seen easily in linear, by the linear response. And then there's this issue of controlling these phases at high speeds and possibly, you know, with a view on device applications. And I'm not sure how far we'll be doing about this in the near future. So let's think about these materials and how they respond to light, what the optical response of these materials are. So we'll be thinking about Q-bridge superconductors, but I won't be saying too much about this because we'll be talking about nonlinear optics today. So let's see, a lot of nonlinear optics has been done in the visible and near visible, and the reason is that it's easy to do. You can buy lasers that work at 1 eV, 2 eV, and you can, you can get very intense fields, and lots of work has been done. Typically, these responses are connected to excitations between different bands. So they will either create excitons or they will create transitions between different orbitals, and they're on relatively high energy scales compared to the energy scales they were interested in, and that regulate the energetics of the underlying symmetries that we're interested in. Okay. And so, just to remind you, excitations at 1 eV are excitations of more than 15,000 Kelvin, so far higher than room temperature. And so there's other areas of the optical spectra, of other regimes of the optical spectra. For example, the mid-infrared range, where phonons are, or the longer wavelengths, the milli-eV terahertz range, where collective orders respond, that have not been studied very carefully in the nonlinear response. And the reason for this is that it's hard. It's hard because you need to, it has been very hard to generate mid-infrared and terahertz pulses at sufficiently strong fields that one could drive this response. Dynamically, this is part of nonlinearly, this is part of what we have been working on over the past few years. So if you came to the last couple of talks I gave, here, I told you a lot about the nonlinear excitation of phonons, how you can drive a certain mode, which to large amplitudes, and how you can deform the lattice of a solid strongly, and look at how energy flows between different normal modes, and how you can control in this way the electronic properties of the system, perhaps looking at electron-phonon coupling in a new way by driving phonons strongly and controlling directions. Today, I'll be telling you about nonlinear excitations of these collective orders, or let's say of the order parameter of superconductors. Okay, and we will talk about high TC superconductors. I'm not sure how many of you know enough about the details of this, but all of you know that specific oxides of copper have been shown to superconduct at temperatures that are anywhere between a few tens of Kelvin and about half of room temperature. So it's really very high temperature superconductivity in which the resistivity becomes exactly zero at below this transition temperature, and the well-known Meissner effect is also observed. And these are oxides in which copper is in copper and oxide planes are believed to contain the essential physics of the transition to the superconducting state, and then coupling between the planes is a weaker effect that occurs because of tunneling. And so one develops three-dimensional superconductivity basically because pairing in the planes and the formation of an order parameter in the plane is shared between the planes because of tunneling. Okay? So everything that I'm going to discuss today starts from this picture. Let's think of the planes of cuprates with this is an order parameter, this is the superconducting order in which we can depict as some sort of vector with a length that is proportional to the number or is related to the number of pairs that one has condensed, and then some phase of the order, which is this coordinate around the Mexican hat. The most important thing is that the planes, because of tunneling, the phase of the order parameter is correlated. The phase of the order parameter in this plane tends to correlate with the phase of the order parameter on the other plane. Okay, so there's a phase stiffness perpendicular to the planes that tends to align and these orders. Okay? And the microscopic physics that I'll talk about today will be thought of in terms of the Jefferson coupling, the Jefferson equations. So the Jefferson equations describe how Cooper pairs tunnel between two superconductors through an insulating barrier. And the two equations tell you two things. They tell you that if I consider now these are my planes and these are all the orders, and let's assume that all the orders have the same, all the superfluids in the planes have the same density. What they tell me is that there will be no current if all the orders have the same phase, whereas there will be a phase that is, there will be a current perpendicular to the planes that is proportional to the sign of the phase difference between these guys. And the second thing that we need to think of is how the phase of advances in time, and hence the current and all the parameters. And the second Jefferson equation tells me that the phase difference between two planes advances in time with the time integral of the voltage, basically the voltage drop, basically the vector potential of an applied field. Okay, so this is the basic of the physics that we'll talk about. And even put simpler, we can think of this coupling if I look at the I know that these planes are capacitively coupled, and the tunneling can be thought of as an inductance. And the most important thing is that this inductance has a strength that is proportional to the inverse of the cosine of the phase difference. Okay? So this is clearly a highly nonlinear electrodynamic problem because remember the phase advances in time with the voltage and the phase changes the inductance, and hence there will be. And this is and the phase in some of these cuprates is very sloppy, which means that for very small fields I'll be able to wind the phase a lot between the two planes, and I'll be able to look at this nonlinear phenomena very easily. So let's see. So if I think about the optical properties of these materials for very small fields, say fields that are almost zero, then what will happen is that this phase difference will be very small. The cosine of a small number will be about 1, and this will be an LC couple. It will be an antenna with a finite resonant frequency, and basically the frequency of this antenna will resonate at a frequency that depends on 1 over the square root of LC, where L depends on 1 over the critical current. So I'll have a resonance that tells me how strong the superfluid density is perpendicular to the planes. And this is routinely used when you do linear optical spectroscopy. You will see a very clear edge in reflectivity, which people call the Jefferson plasma resonance, that can be used to diagnose the strength of the interlayer tunneling between these planes. And this is the first experimental curve that I'm showing you. In our experiments, what we do is we use terahertz radiation, and these are basically half-cycle pulses with a period of about 1 picosecond. So these will be radiation at about center frequency of 1 terahertz, period 1 picosecond, and a bandwidth of about 100% because it's a single cycle. And so we'll have this pulse. This is linear, very low fields. This pulse impinges onto the superconductor with the electric field perpendicular to the planes, and it will be reflected, and there will be, of course, this will be changed. And what you will see is that below TC, this is lanthanum strontium cuprate at about 16% doping. This is a 40 Kelvin superconductor at optimal doping. What you will see is that the re-radiated terahertz field, which is reflected, has a very clear ringing in its wake. These are the Cooper pairs tunneling backwards and forwards from the planes between these two capacitively coupled planes. Okay, this is the frequency of the LC circuit, because this thing here behaves like an antenna. Okay, this is known, and these are like I'm going to spend a second to describe these optical properties because they will be useful later on. This is the way I do the measurement. Above TC, I get a resistive response because there's no tunneling, there's not much ringing. Below TC, I see this ringing, which I can then take these curves, of which I know both amplitude and phase, and extract the optical properties, n and k, epsilon 1, epsilon 2, whatever you want. So I can show you, for example, that...
Sorry, 0 is with the center of the pulse comes out.
Yeah, it's not that important actually, because this is at this stage you just come in with a pulse and then you measure how it you can move that wherever you want.
It's radiating back.
It's radiating back. It's a linear. So you can put 0 where you want. Let's see. So you can extract the real and imaginary part of epsilon, and so you will see the response of a plasmon, because you have epsilon that is negative and tends to diverge towards 0 frequency, and it crosses 0 at the frequency of the plasma. This is, and then if you plot the modulus of the reflectance, you will see that above Tc, where you have the resistive capacity coupling, you have no feature. But below Tc, you see this plasma edge, which is at the frequency in which epsilon 1 crosses 0. Again, I'm telling you about the things you all know. And then another important parameter, another important set of quantities to be kept in mind here are conductivity. So this number epsilon, as you know, it gives you the proportionality between the polarization and the electric field through chi, which is related to this. Whereas this gives you a proportionality between the current and the electric field. And what you know is that the real part of sigma, the dissipative part of sigma, is 0, and out here we'll have a gap, and down here we'll have a delta function. Whereas the imaginary part, which is the reactive, the conductivity will diverge like 1/omega towards 0 frequency, where you will, because there's a delta function at 0 frequency. Okay, so these are the features of a superconductor, and the amount of divergence of sigma 2 will tell me how many, how big was my or dense is my order parameter. What is the superfluid density perpendicular to the planes? Okay, these are the optical properties. They all say the same thing. We'll be thinking about. So this is in small field. Now presumably, let's think that I could have a strong enough terahertz field. Up to a few years ago, this was not possible. There's been advances in the way we generate these pulses that make it possible now to generate many megavolt per centimeter fields at, say, 1 terahertz. So, and whereas before it used to be a few volts per centimeter, so you could only do. So if I can do this, and if the field is strong enough, what I can do is I can wind up the phase. I think I'm gonna, does anybody, okay, I think I can wind my fingers. I can wind up the phase between the planes by a large, oh, this is like it's how you fix a laser. Yeah. There you go. Can tell you right here. So you can move the phase by a large number compared to 0, and that inductance, because the cosine will become a small number, the inductance will become a large number, and hence the 1 over square root of LC will move to the red. Okay, Jose, don't worry about it. I think I'm agitated enough. Don't worry about it. It's I move around enough, and I think I can. Thank you. Okay, so I will have now a more complicated situation. Obviously, when the phase is pi half, the circuit is open, which means that there's no tunneling, or sort of that there is interference between this tunneling that goes exactly to 0. This is a pi half Jefferson junction. When the phase is pi, inductive coupling is 0, so I'll have a resistive coupling between the planes. When the phase is pi, if I apply a voltage like so, there will be a current going in the opposite direction because I'll have a negative inductance, and etc. Okay, so what I've just described to you is the AC Jefferson effect, which is you can think of, and this is something that could not be observed. People had a sense up to a few years ago, or it's reasonably well known that the layers of cuprates are Jefferson coupled, although the AC, the rotation of the phase and of the current due to the AC Jefferson effect could not be seen. Okay, but in principle, if I apply a voltage and I wait long enough, the current will oscillate between the planes backwards and forwards. Okay, there is some evidence. There has been some evidence that if one would grow mesas of Pisco of one particular type of superconductor, one could apply a DC field and generate microwave or terahertz radiation. Okay, but this is hasn't been studied too much. Okay, so let's see. For various reasons, we've become interested in trying to manipulate the phase between the phase of a cuprate superconductor at ultra-fast rates. And this had to do with being able to move them on the time scale over which they fluctuate. And at some point we convinced ourselves that we could do something by manipulating these phases, because the way these phases fluctuate, at least close to the critical temperature, are known to have influence on the transition. So this was our original motivation of why we became interested in manipulating these phases at high speeds. But basically the bottom line is that if you want to flip the phase between two layers within 1 picosecond, say, or you want to rotate it by pi or pi half, and you have a 1 picosecond pulse, you can do a back of the envelope calculation, and you need fields of order 100 kilovolt per centimeter. Obviously it's very difficult to do this in CW because the thing is going to heat up. In DC it's going to heat up and you lose. So this needs to be done in a short pulse. But basically this is the field that you need. So I'm going to tell you about 2 or 3 experiments that have got to do with this, and some of those are more sort of to get warmed up, and in the last part I'll tell you something that we have learned about this. Doing this. Okay, so the experiment is going to be the following. Now Bertie, I'm going to tell you about all the pump probe delays. Now there's going to be 2 pulses. The first pulse is going to be let's see, on the left-hand side, I have the reflectivity of the sample. This is lambda Strontium cuprate, but it could be something else. And I'm going to have a pulse, which is a half-cycle pump, which is broad enough, but it's an essential frequency that is far below the resonance frequency. So it's being evanescently screened into the material, and it doesn't propagate into the material. Thank you so much. It's going to be evanescently screened, and so this is going to be the pump pulse, which will exponentially decay into the sample in the direction parallel to the planes, which is where the pointing vector is. And then there's going to be a probe pulse, which is a far broader probe pulse, which will monitor the position or the advance, the change in the optical constants as a function of time, as the time evolves. Okay? So let's see, now I'm going to repeat what I said before. The probe pulse alone will be discussed in terms of either the reflectivity, which is what I showed you as an edge at the plasma frequency, or the conductivity. So remember, the important thing is going to be the imaginary part of sigma, which in a superconductor goes up toward low frequencies, whereas it goes towards 0 in the metal. And the real part of the conductivity, which is 0 at finite frequencies below gap in a superconductor, but becomes finite in a metal, in which might be true response. So there is a transfer spectral wave as I am moving between a superconducting interlayer coupling and a resistive interlayer coupling. Okay, now this is what I see before I pump at equilibrium. So I'm going to show you now 2-dimensional plots in which I scan the relative time between the 2 envelopes of the pump and the probe. And then I'm going to use another pulse to measure the frequency response of the probe. So I'm going to show you 2-dimensional plots in which the frequency response of sigma 1 and sigma 2 evolves in time as a function of the pump probe time delay. Okay? And the pump pulse is intense and the probe pulse is weak.
So roughly, how much of phase rotation do you get from the pump?
So, we did the experiment, and the goal was to try to manipulate the phase. So let's look at the real part of the conductivity. The time goes from low, below, to high, above. So negative time delays is when the probe comes, thank you very much, comes before the pump, so it probes a sample that hasn't been excited. And positive time delays is when the probe is measuring at positive time delays. The real part, the negative time delays, because I'm probing an unexcited superconductor, is 0. Whereas the imaginary part diverges like 1 over omega because it's superconducting. So what you find is that at some time tau 1, the real part becomes finite and acquires this Drude-like shape. Whereas at the same time, the imaginary part becomes 0. That's fine, I've broken the superconductor. But then if I wait some time, I am back in a superconducting state where sigma 2 diverges and sigma 1 is 0. and then I wait some more time, and I oscillate between metallic and superconducting coupling between the planes as a function of time. Okay, I either have this sigma 2 diverging and sigma 1 flat, or sigma 1 being a Drude-like large number and sigma 2 going down. Okay. And also I can actually fit, what I can do is I can look at how 1 over omega this number is, and this tells me about the interlayer coupling between the planes.
Yeah, just to make sure, in the analysis, you still assume that whatever you extract as a reflected light at some frequency came from the probe at the same frequency. So we do not include mixing.
That's right. That's right. I am assuming that the response, that the response of the probe is linear in a sense. That at each time delay, I can probe over a given frequency spectrum as if the sample was at rest.
Yeah. The time delays are comparable to the frequency resolution, or
Yeah, I mean.
So that's sort of confusing. It looks like you're violating.
No,
Heisenberg's
okay.
principle.
Well, the frequency resolution or the frequency spectrum?
Well, so
It's oscillations, I guess what to say, let's say you have some dynamics, right?
Yeah.
Phase.
But let's say, okay, I'm going to show you that. We can go back. Can we go back to this? I'm going to show you the exact numbers now. But,
okay.
so let's see. We're going to get back to this. I'm not trying to. I'm not trying to.
Okay.
So anyway, so here I am taking. I'm not sure if this helps, but here I am taking the integral of the pump pulse, which is the driving field. And I am and I am stretching it up and down to above, between pi half and pi in this case, and I can fit the
So
super.
this is your estimate of where the phase is.
Exactly.
So the phase first it goes negative and then it goes positive.
Exactly. And all I need to do is I take the experimental, the integral of the experimental pump pulse, which is some field, and I can fit the superfluid density as a function of time with only one free parameter, which tells me how far, because I don't know, of course, what the voltage amplitude is. And this number, now going back to your question of the phase, this number is basically a number that I extract from omega sigma 2 at a frequency that is high enough so that the time frequency, time delay to frequency is reliable. Because sigma 2 is diverging toward low frequencies, omega sigma 2 is a constant, so I can take it at a high enough frequency and trust that things are okay. But be as it may, I can take this, I can fit with only one free parameter these oscillations in which the superfluid density goes up a little bit, goes down a little bit, goes up, then goes to 0, then comes back up, and yeah. So this is this. And what I said was that this frequency should be dependent on the intensity of the terahertz field. And so what we showed was that the frequency of oscillation, okay, if I scan the peak electric field pump strength, and I plot a frequency, what I show is that up to a certain threshold, there seems to be a frequency that is not very, that it kind of follows weakly the pump frequency. But then it becomes a linear function of the peak field of the pump, as I would be expecting from the AC Jefferson effect. So this is not surprising. It's in a sense, we haven't really learned very much, but this gives me, okay, another thing that I want to tell you actually now that I see the next slide, is that if I do the same experiment in the plane, now I'm applying a field perpendicular to the planes, because of course I could be changing the superfluid density in the planes, but in the plane I can plot real part of sigma and imaginary part of sigma, and these don't change very much. So it seems that this experiment is indicative of a time-dependent oscillation between superconducting, resistive, superconducting coupling, as if I was modulating the dimensionality of the superconductor. Okay, so this is,
field.
Come again? this is like, let's say that this is the field, and
The electric field is not perpendicular to the plane?
the field, the pump field is perpendicular to the
Right,
planes.
that's what gives you the oscillation.
Exactly.
I thought you said, okay, right.
Yeah, exactly. No, sorry. I see oscillations.
But the field is perpendicular to the plane. not
Both pump and probe with the field.
the
Exactly.
field, right.
If I now pump perpendicular to the planes, but I probe in plane, nothing seems to be happening to the superfluid density in the planes. So this is a demonstration of an ultra-fast AC Jefferson effect in the planes of cuprates that everybody knew they were Jefferson coupled. But this is a nice first experiment that to discuss the nonlinear physics of this. So let's get there's two things, and let's get a little more interesting. So up to now, what I've shown you were excitations in which my pump was at a frequency at which this was which was far below than the resonant frequency of the LC coupled planes. What I can do though is I can tune the pump. In reality, what we did is we changed the superconductor, we moved the plasma toward here. Where the strong pump is resonant with the frequency of the Jefferson coupling. So let's think about a little bit about our nonlinear Jefferson problem now. What I have is I have this inductance which depends on the inverse of the cosine of the phase. I have a field that I apply that goes with some sort of sine omega plasma. I have a phase. Remember, the phase goes with the integral of the field. So I have a phase that at this phase between the plane advances in times as some number, which depends on E0, times the cosine of omega t. And so, because the inductance had cosine here of the denominator, I can easily work out a situation in which the interlayer coupling has this form. So I have this, that the interlayer coupling as a function of time will be the initial interlayer coupling, which is reduced by some on average by some amount that depends on the square of epsilon 0, theta 0, times a modulation that goes at twice the frequency, the eigenfrequency of the couple. So repeating this, so let's see. When I'm in linear response, I have a phase that oscillates at omega, and the oscillator strength that couples the planes is constant. Whereas when I consider a strongly driven resonant phase, I have a phase that oscillates at omega and an oscillator strength that oscillates at 2 omega, where the oscillator strength is the position of the phase. Okay? So this can be very clearly seen if one looks at a similar pump probe experiment as the one I was telling to you before, and one looks at the ringing at long times when the phase is freely evolving. You'll see very clearly that if you pump with an electric field at half a terahertz, at 500 gigahertz, you see oscillations in the oscillator strength that I have extracted by some appropriate fitting at twice the frequency of the drive. Okay? So is this interesting? The reason why this is interesting for at least a couple of reasons. Firstly, is that this is I can think of this is equivalent to the well-known mechanics problem of a child that sort of oscillates on the swing at twice the frequency of the swing, yeah? And can be used as a parametric amplification of phase fluctuations. Okay? And this is actually seen very clearly if I now plot the spectrum. This is a spectrum measured in the time domain. This is the probe pulse. And what I see is that at the correct phase difference between the pump and the probe, I either get an amplification of phase fluctuations, when I turn the pump on, or a de-amplification of the phase fluctuations at regular intervals for the relative phase between the two. Okay? This is seen even more clearly if I now, instead of plotting what I just showed you, which was slightly qualitative, I now plot a loss function, which is a quantity that tells me where epsilon crosses 0 as a function of time. Okay, so this The loss function is a quantity that is positive in a dissipative system, but is negative if you have an amplifier. Okay? And so this is now the experimental data. This is the loss function that is related to the Jefferson plasma coupling at 500 gigahertz as a function of pump probe time delay. And what I'm showing you, in blue, I show you positive loss functions, and in red, I show you negative loss functions. And the loss function, here I'm starting to pump it, becomes negative, then it becomes positive, negative, positive, negative, at 2 omega, where omega is the eigenfrequency of the LC couple system. So this is interesting for various reasons. It's interesting because, yes?
You even use this language, right? Because we no longer have translational symmetry, so my sigma is really a function of 2 separate times. It's not a function of the time difference. Because sigma of omega, epsilon of omega, the Fourier transforms of sigma of t, where the relation between electric field and current, and that depends only on the time difference. But if you have some oscillations, you cannot even use this language, right? Because the relation between current and electric field depends on both types.
You know, I understand what you're saying. This is actually a good point. I need to think about this, but it sounds like you're right. So maybe using the loss functions of these equilibrium quantities.
Right.
And how non-correct it is, I don't know. But,
right.
But there's,
when you pump, somehow when your try was very slow, that was probably okay. It was like a quite a steady state. But now everything is sort of oscillating on the same time scale.
Yeah, I need to think about this more carefully. But let's say this thing that I call the loss function now in this case, assuming it goes from positive to negative, and at least that's an observation. Now, whether I should call this loss function or not, I'm not sure. Okay, but clear. Okay, yeah, point taken. We need to discuss this. But the important thing I would say is that the phase fluctuations that I showed you, in time they get either amplified or de-amplified. And the reason why this is potentially interesting, aside from doing this, is that in principle this could also be used to squeeze the fluctuator, to do quantum squeezing because of the order of this nonlinear coupling of the phase fluctuations. And again, in a world in which phase fluctuations are bad or good for superconductivity, this is an interesting way to try to. We haven't done this because this would be a whole, but we've been thinking about trying to find driven states of cuprates in which one could manipulate and squeeze the phase. Obviously, the phase fluctuations of phi and phi dot would oscillate at 2 omega. We get larger or smaller and larger or smaller at 2 omega. But maybe there's an interesting steady state that one could consider. So this is where this project was at, and we haven't been working too much about it, but it's there. Okay. So I'm going to tell you one more thing about this, and this is something I talk I've given once already. Let's get serious. How can I make use of nonlinear THz spectroscopy for something important that is related to the microscopic physics of cuprates? Okay, and now cuprates are renowned to have these ever more complicated phase diagrams appearing in the literature. But one of the key issues that has been discussed for a very long time about the physics of cuprates is the interplay between this superconducting state, which happens at low temperatures for doping anywhere between, say, 5% and 20%, and what happens above the transition temperature, especially in this underdoped region, where at least 2 things happen, or more than 2. One is this mysterious pseudo-gap phase in which one finds many features of the gapped superconducting state without superconductivity, and one is the appearance of these charge density waves, or stripes, or striped phases that appear to compete, or coexist, or help, or not superconductivity. So, and one of the systems in which this discussion of the competing charge density wave has been especially important has been in the single layer, in the case of single layer cuprates, like the barium doped lanthanum cuprate, in which one knows that one has a rather strange phase diagrams where instead of having a single dome, where superconductivity takes place, one has a double dome structure, and close to this magic 180 doping, one finds that TC is depressed all the way to almost 0. And at the same time, one finds the formation of these charge stripes, charge and spin stripes, that are arranged in a crisscrossed pattern as one goes along the z-axis. And this state appears to reduce the homogeneous three-dimensional superconducting temperature. Actually, certainly reduces the homogeneous superconducting transition temperature. There has been a lot of conjectures, most recently, that have after some very beautiful experiments in which one found that, in fact, even in the strike phases above the transition temperature, one could find very high conductivity in the plane and low conductivity perpendicular to the planes. There's been some conjectures that have posited the possibility of a superfluid superconducting order that would evolve along the planes with the pitch of the stripes. So this is the so-called pure density wave state, and this was work done amongst other people by at first by Ellsberg and Kivelson and various other people at Stanford. Okay, so there's this sense that maybe one should think about these strike phases as coherent states in which superconductivity perpendicular to the planes somehow disappears. Okay. There's been also STM measurements. I won't get into the details. I will go back to the reason, to how we should think about these putative superconducting stripes. So even assuming that this pair density wave state were to be completely coherent, if I were to look for supercurrents perpendicular to the planes of the types of the ones that I've described to you due to the Jefferson effect, I would end up with an average with an average of a completely zero current. And the reason for this is that if one looks at a model for this pair density wave state, one should consider a checkerboard array of alternating pi half and minus pi half Jefferson junctions. And this is here pictorially shown here. So in principle, what one has is a situation in which at each one of these neighboring pi half and minus pi half Jefferson junctions, one always has a current that goes up and a current that goes down, with an average current of being zero. And so in all the fluctuations close to equilibrium of this state of affairs are equally canceled out. And hence one may have a situation in which planes are Jefferson coupled, but in which the current is exactly zero between the planes because everything is exactly correlated. Okay? So and for this and many other reasons, this is a frustrated coupling and a hidden there's hidden excitations that I can't see, because even if they're optically active, they're silent because they are let's say the matrix element is zero. Okay, but this is okay. But the point is that with everything that I told you before in mind, maybe I can't see these currents in the linear response, but maybe if I drive the phase with a large enough amplitude, maybe I can find the signature of these. Okay, so let's first think about a situation in which I have a homogeneous order. So this is now a superconductor of the same type as the one that I showed you before. Okay, the first talk where I told you about all the other experiments. So here, there's stripes are very weak, and I have a transition between basically a bulk three-dimensional superconductor and incoherent state. So let's go back to the situation that I described before about the parametric amplification, and let's think about it in a different way. If I think about now this field and the phase that advances as a cosine, I can rewrite the current that circulates in this homogeneous superconductor, and as you will see, because of the order of the nonlinearity, I should have a first harmonic and a third harmonic. That, of course, is not seen when the field is small. Okay? So, so that's, I repeat what I just said. If I pump on resonance, I should see a first and third harmonic. And these are calculations that we did basically solving a one-dimensional propagating using a sine-Gordon equation to try to understand, how this is a single pulse experiment, by the way. I come in with a light and I look at the light coming off. That's it. And so I crank up the field and I look for harmonics of the driving field. And if I now consider the propagation, again, where the electric field is polarized perpendicular to the planes, and the Poynting vector goes parallel to the planes into the sample, and I can predict what the reflection of the material will be if I solve the sine-Gordon equation for the phase with some sort of plasma polariton Jefferson plasma polariton propagating into the material, and then calculating what the re-radiated field is. And if the field is large enough, I will see that the reflected field, this is time, and this is space into the material, will have a first harmonic and a third harmonic component. Yes?
So this is the case with frustrated.
No, this is the case of the 9.5 sample, which is the one where the stripes are really far weaker than anything else. And it's the same also, you see the same at 15.5. This is data that I haven't shown you on the peak of both domes. And so you can see that in linear response I have this edge, and in nonlinear response, if I define a reflectivity, and now I'm not sure what Eugene is going to say, but it was me using all these linear response terms, but let's say the reflectivity defined as the field that comes out divided by the field that comes in. I will see a redshift on average of the plasma. Remember, in the parametric amplification, I had omega p minus theta squared divided by 2. So on average, there is a redshift. There is some parametric amplification here that I discussed to you before, which again appears here again. And then this gigantic third harmonic. This is a third harmonic that is many, many, many orders of magnitude larger than I would see in any other material. And the reason for this is that the phase is so sloppy that it has an enormous optical nonlinearity. A very small field will rotate the phase close to pi half and give rise to a large nonlinearity. And so, you can calculate to other orders what could give you these types of nonlinearities. Another idea would be the non-parabolicity of the bands, obviously, if you think about normal electron excitations. But these are all effects that are far less, many, many orders of magnitude smaller than this. So for the purposes of this talk, we're going to use the idea. This is theory, by the way, not an experiment. We're going to use the presence of a large third harmonic as indicative of the presence of interrelated time. Okay, so we do the experiment, and we do see a very large third harmonic, and we see that the third harmonic at least is compatible with cubic scaling, as one would expect. In this, and also, so it's reasonably similar to what we simulate. You see a redshift, a little bit of a spike here, if you are generous enough, and a very large third harmonic. And we also see that in this case, the third harmonic, if I plot the superfluid density as a function of time in black, and the third harmonic, as a function of temperature, apologies, in black, and the third harmonic in red as a function of temperature, in the homogeneous superconductor, I see that the third harmonic goes away when the superfluid density goes away. So at least in the limit of a homogeneous superconductor, these two guys seem to be well correlated. So let's go in this phase, which is where Tc is about, I forget, say 9 or 10 Kelvin, and above here, this is the region where where it has been posited that one may have the superfluid stripes. So we go here below Tc, which is where the stripes and superfluid order compete, and I still see this very large third harmonic. Now here the plasma edge is shifted to lower.
Is this a single pulse experiment again?
Single pulse. Yeah, so I measured the phase and I just look at, so it's a relatively easy experiment. And then here I see a large effect, and the scales is compatible again in some way with a cubic scaling or some, at least let's say it's not in contradiction with that. What is surprising is that when I go above, even in the stripe order phase and in the charge order phase, whilst the superfluid density drops here at 12 Kelvin, I see this very large third harmonic, really large, also in the normal state, in the state where I have the stripes, okay? And up to now, I've been telling you that we believe the third harmonic is indicative of Jefferson timing. So let's see. Well, how can we think about this? Now, remember, before, all I talked about was a homogeneous order in which I would have only one type of plasma, which would be an acoustic type plasma, in which all the phases are independent of position and they oscillate homogeneously. Obviously, in a situation in which I have these crisscross states, there's going to be at least two modes because I reduce the symmetry. And I can discuss this in terms of what we call a phi zero mode. This is a mode that is optically active, so the phase can be driven by the optical field, even at small amplitudes, but that results in currents that are oppositely phased. So this is an optically active but silent mode. And then this is the phi pi mode, which is a mode that by symmetry doesn't couple to light, okay, at linear. And I can think of this as a situation in which the phase is being driven by my pulse, and this would be the equation of motion of the phase of this mode with the currents going to 0, and the second mode will not be driven by the light. Okay? So, and this first mode, as I mentioned before, although the phase is oscillating with the sign, this will drive current fluctuations that cancel out and end up being 0. Let's think about what happens if I now drive the phase to large amplitudes. Of course, I can write down the energy. I have these two terms because of the symmetry. One is square, one is odd, and the other one is even. So the lowest term in one case goes with the square, and the other case goes linear. But there's also a coupling term between the two. Okay, so the point is that I have these two modes that in their response, in linear response, and all expansion terms individually will not give me currents. But there is also a term in the energy and in the equation of motion that couples the two, that couples these two phases. Okay? So now, if I drive with a strong field, I will have that the first mode, the phi 0 mode, will still oscillate like the cosine and will give me 0 currents. But the second mode, the phi pi mode, will now be driven by the square of the first mode because of the coupling. Okay, so I'll have all of a sudden, because of harmonicities, I will be driving this, and I will be driving these two phases, both of them. And if I then consider, like, oh God, this is very embarrassing. This was the most important. This was the most important slide. So okay, you're going to have to imagine what I'm about to tell you. If I calculate all the currents using the Jefferson equations, because I have a mode that goes at omega and another mode that is pumped by the square of the mode that goes at omega, I will be mixing modes at omega and at 2 omega, which will give me a response, which will give me radiating currents at omega and 3 omega. Okay? And I do apologize for this, but this is it basically starting from these equations of motion, where I have the optically active mode that oscillates backwards and forwards and has 0 currents, and the second mode, which is being driven by the square of this. This goes at 2 omega, and this goes at omega. I mix them together. I go through the sign of the Jefferson equations, and this gives me first and third harmonic.
Do you have a sort of like hand-waving argument of why it goes to the square?
Yeah, this is because of symmetry. Because one is odd and the other one is even, and hence one will have linear. One will have the lowest order will contribute to the energy linear, the other one will contribute to the energy square.
I may be confused
Yes.
about the direction, but if something has no current, why is it coupled to the electric field?
Because the electric field, remember, the second Jefferson equation tells you that the phase difference between the planes couples to the integral of the electric field. Okay?
Yeah.
But you can still have a situation in which you have if you have a pi half and a minus pi half Jefferson junction next to the other, one another, locally what I will have are currents that are being driven by these phases.
Locally.
But once I integrate spatially, the overall current will average out to 0. So it will couple to an electric field, but the space integral, this is the argument of why the pair density wave doesn't give me excitation. Yeah. So the argument here is that if you do all these numbers, you will end up, and this is a calculation by Ludwig Manteg's group, who has helped us sort out this last part of the excitation of the response. And you can see that if you consider a situation like the previous one that I told you about, in which you have this checkerboard pattern of pi half and minus pi half Jefferson junction, you drive them strongly, you get no response in linear response, but you will see a very strong 3 omega response when they're strongly driven. So the data are by and large consistent with a situation in which the superconducting, in which the stripes may be superconducting, and maybe there's something to this very model. And of course, what is really very interesting would be to try to extend these studies to other materials. Well, firstly, we're developing a phase diagram for this putative pair density wave state by looking carefully where the third harmonic appears up to which temperature. And in principle, one could go to other systems like YBCO or other situations in which one has charge density wave and try to do studies of this type. Obviously, the effect is much easier to interpret if you're in a single layer situation. Once you have multiple layers, you start having multiple Jefferson modes, and everything gets a little hairier. So I'm going to say this is all I wanted to tell you. So I told you about three things. One is about just basic learning how to manipulate and flip the phase between of cuprates. One is about showing that in principle you could parametrically amplify phase fluctuations perpendicular to the planes, and one in which one could use strong field terahertz responses to reveal frustrated excitations that don't appear to linear response. Okay, so important people. So let's see. Sridhar Rajasekaran is the guy that has done most of these experiments after Andreas Dienst, who was my student in Oxford, and so Sridhar is a postdoc with me. Michael Fechner is a DFT guy. He has helped us actually. I haven't shown you any data, but he's helped us sort out all the what you would have instead by simple band structure of the A calculations, and what other terms turn out to be small. The samples come from Brookhaven, and we've had a lot of help by, especially in interpreting this last data by Ludwig and his postdoc Junichi Okamoto. And I'm going to leave you with one more thing, where there's a lot of other things that one can do with this nonlinear Jefferson coupling. We've written a number of papers with theory colleagues in Oxford and Hamburg, where we showed that one in principle could cool phase fluctuations between the planes by using various combinations of those techniques. And also another piece of work that I didn't have time to tell you, in which we discussed the excitations of breather excitations and of vortex, what we can also call traveling vortex anti-vortex pairs in driven superconductors using different techniques, and this would have been a talk in itself. But in principle, I think I said at the beginning that this is an area that nobody's interested in. But I find it extremely rewarding to be able to just look at this really highly nonlinear system of a prototypical quantum material, and how one can try to manipulate the phase in time. So I thank you for your attention, and I hope something came across. Thanks.
So, like when you're plotting the E in and the I out, so in principle these are complex quantities.
Yes.
Now, the E, I guess if it's a symmetric pulse, it's real, but I would think you really want to. Were you plotting there just the magnitude?
I just took the modulus. I took the modulus I threw away information to show that data. We have obviously small r plus I, small r1 plus I, small r2. And that's how we extract typically epsilon 1 and epsilon 2. But in this case, we just wanted to encapsulate, to somehow find a number that was, yeah, absolutely. So this is actually one of the beauties of terahertz spectroscopy done this way compared to regular sort of optics measured with spectrophotometers. That one gets I mean, without ellipsometry and even with narrow band, you can pull out the complex quantities.
Question. So this system is just like an extended Jefferson junction.
Yeah.
And there was like an old history of people looking, and they were studying solid bonds. So can you get some interest in
Extended along this direction, or okay? Obviously, there's an issue of which I've completely disregarded of synchronization between multiple layers. I have decided that there are only 2 layers, and I've always simulated everything. So obviously, there's issues there that we're not discussing. But also, these are long junctions, obviously, in which you have a propagation. The only situation in which and in some cases, for example, that's the reason why we solved the Sine-Gordon problem. So we look at the nonlinear plasma polariton as it propagates in. Okay, the clearest demonstration of this is discussed in this paper, where we this thing doesn't work, where we discuss the possible excitation of this breather of these breathers that are related to these nonlinear excitations of the phase that then propagates and form plasma solitons, so to speak, and propagate in. Okay, so this is what I'm depicting there. This is again the phase as a function of space and time.
Colored in blue, red.
Yeah, these are my breathers where the phase is oscillating. Unfortunately, I didn't discuss this, but we did that in that paper using a narrowband terahertz free electron laser. We were able to to generate and study these effects. You know, it's a little bit of a field, something for specialists to study this nonlinear. Yeah.
So I have a comment regarding the loss function. I think the language of solids is weak field CW. So it's not only the loss function, it's pretty much everything we use to describe solids is false, basically. It's broadband, impulsive responses are very different than what the language that we use currently to describe solids. So it needs a rework, not only for the loss function, but for pretty much the dielectric functions, the absorptions, all this stuff needs to be.
Okay, let's see. I actually disagree with at least half of what you said. Because, so there's two things. So what Eugene was concerned about was a situation in which you were saying, I'm amplifying parametrically, which means I am, even in the probe process, because there is a pump, there is a field that is oscillating and pumping this parametric, you know, there's a term in the material equation, I am mixing omega-1 and omega, pairs of omega-1 and omega-2s in my response, and you gotta be a little careful. You can't, but what you said, I think, is not right, because in general, because in many situations in which with an impulse excitation you generate a time-dependent evolution of the optical constants, you can still define optical constants at frequency much higher than the rate of change as being quasi-static. So there are some limits in which epsilon 1, epsilon 2 as a function of time, and sigma 1 and sigma, or these things, are still applicable, as long as you look only at frequencies that are fast compared to the rate of change of the signal in which the material is quasi-static. But obviously, once you start mixing things in amplifiers, then you really need to be very careful. And I have to think more, you know, better about what he said here. But that clearly was he definitely had a point.
Yeah, that, I agree with that limit. The other question that I quite didn't get, maybe it was a discussion, is the second order dependence on the phase. I quite don't...
Say that again,
The second order dependence on the phase. Once you start driving current in these two planes, I quite don't understand where that comes from. And at the end, the nonlinear response is very different than the nonlinear response that you will see in classical nonlinear response that depends on the susceptibility and so on and so forth. In this case, you are...
No, but I mean, so remember, basically all the issue was that you have an LC coupled, you have an LC oscillator where the inductive coupling depends on the inverse cosine of the phase, and the phase depends on the integral of the field. And so you can see immediately this is a forward mixing type nonlinearity. In optics, you would call this a third order nonlinearity, which then has these phenomena like parametric amplification, squeezing, this and that. So in that sense, I think that's about right. Whether I should call it epsilon 1, epsilon 2, or sigma 1, sigma 2, I don't know. But I think this is reasonably clear.
Okay, let's try again.